This is the fourth video in a series of introductory videos introducing differential equations. So in this video, I'm going to talk about phase lines, but before getting to phase lines, we have to jump back to the topic of the previous video, which is slope fields. So when you have a slope field for an autonomous differential equation, these have a special property, and that property is what allows us to define a phase line. Okay, so what is that special property? So let's just write down a reminder of what autonomous means. So here, autonomous means that if we're looking at the equation dy dt equal some function of, and now in general, if the function on this side can include a t and a y, but for autonomous systems, the t is not explicit. There's no t dependence on this side. And so what that means is we can actually remove that t and we just have the f of y function. So autonomous means for dy dt equal f of y, the function f, is independent of t. So let's look at an example. Here I'm going to use the logistic equation dy dt equal, and I'm going to choose, just to make things a little bit simpler, I'm going to use what we call the non-dimensional form, and in that case we'll set r equal to 1 and k equal to 1. So we get y times 1 minus y for the function on the right hand side, and you can see that the slope of y depends on the height of the function y value, but not on the time. So there's no dependence on absolute clock time. And what that means is that when we draw the slope field, there's going to be the special property that we're going to take advantage of. Okay, so before I get to the slope field, let me just draw the graph of y1 minus y over here in a small version. So here's the y-axis here, and here is y1 minus y on the vertical axis. So we could call this axis f of y, but just to make it clear, I'm going to put in the actual function there. And that's a downward quadratic that goes through 0 and 1. And let's put in a couple features. So here at 0 and at 1, the value is 0. And then right in the middle here at 1/2, we reach a maximum value of 1/4. Okay, so those are going to be useful features. The other thing is that the height of the function between 0 and 1, the height of the function is going to be positive, meaning that the slope will be positive. So the slope of y, dy dt, has a positive value with the largest positive value when y is equal to 1/2. That's right there. And then outside that interval for 0, for x, or for y below 0 down here, we have negative slopes, and out here we also have negative slopes for large y values, because the function y1 minus y is below the y-axis. All right, so that's going to be a useful reference tool for making the slope field. So let me put that in now. Here we have the slope field. I'm going to put the y-axis here and the t-axis here. And on the t-axis, mark a t, up here a y. And what else do we want? Okay, so let's put in some of the special values that we've already identified. Y equals 0 is a special value, and y equal 1 is a special value. And so with those two, I'll start drawing in the slope field. So let's put in the slope field along 0. When the y value is 0, so here's the y value, and a value of 0 gives me a height of 0. In other words, there's a 0 there and a 0 there. That means dy dt is equal to 0. So that means whenever the y value is 0, the slope of any function, any solution has to have a 0 slope going through that y value. So I have all along here, we have 0 slopes. And you can already see that y equals 0, if I started with an initial condition right at y equals 0, I can fill in a curve that goes straight along the axis that always has these little slope elements tangent to that line, the y equals 0 function. So we've already found one solution to this equation, and you can see that y of t equals 0. When I take its derivative, that's clearly 0, and when I plug in 0 here and here, I get 0. So that function satisfies the differential equation. So the next easy one is the y equal 1 height. So if the height of any solution is 1, at that moment, the slope of the function has to also be 0, because we have a 0 from this part, right? If I plug in 1 here and 1 there, this becomes 1 times 0, so dy dt has to be 0. So all along that line, y equal 1, we always have to have these 0 slope lines. So what that means is anytime we try and draw a solution, let's say, oh, is this a solution to our differential equation? No, because as the function goes through y equals 0, the slope of this thing is not 0. Or up here, both of those violate the differential equation. So that could not possibly be a solution. Okay, let's fill in more slope lines before we make any more attempts to figure out what this thing looks like. So, one interesting point that we've already identified is when y is equal to 1/2, we have that the solution, any solution, has to have a slope of 1/4. So I'm making this like, maybe this looks more like a slope of 1, but let's just think in our heads that the t-axis is scaled in such a way so that this is slope 1/4. And I do that just because I'd like to have enough room to make a smaller slope above and below, because when we look at this graph, for the value of y equal 1/2, which is this line all the way across here, the slope will always be 1/4. But then if we go above 1/2, the slope will be slightly less than 1/4. And as we get closer and closer to y equal 1, the slope gets smaller and smaller. And once we get there, the slope is exactly 0. So let's fill that in. And so in here, somewhere between 1/2 and 1, we have to have a slightly smaller slope. And every one of these has to have the same tilt to them because they're all at the same y value. No matter what the y value is, no matter what the t value is, this function did not depend on t, so we just take the value y and we find the slope at that point, and that's what the slope has to be throughout. If we go a little bit higher, let's say we go really close to 1 up here, then the slope is even closer to 0, so it's lower angle. Not quite 0, but somewhere between the one below and the one above. And similarly down here, we have to have lines that come to a smaller tilt. So these are all little, what we call slope field elements. And they're all lined up nicely so that their steepness is all the same in the horizontal direction. If we go to different t values, the y value is the same. And now if we go above 1, we have negative slopes. So here we have a slight negative slope. And if we go higher in the y direction, we get steeper negative slopes because, so we're above 1, and we go to a higher y value, we had a negative slope. We go to even higher, we have a more negative slope. And so we get steeper, 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 and so on. And we have a similar thing happening on the other side of 0. Again, these are all negative, and as we get further and further from 0, deeper into the negative numbers, the slopes get steeper and steeper. So what I'm going to do here is I'm going to just draw 1, 2, 3, 4, and then I'm going to catch those all with a loop. Oops, well, I guess I can put that back with a copy paste. So we get those back here, but then we can add in more. And now I'll just take advantage of exponential growth and make more and more of these. And so we can see a lot of what this function, any function that's a solution will have to do. Okay, so let's try and fill that in. So if we start with an initial condition, let's say up here, we have to follow the slope field line. So it starts off slightly steep, but as it rises, it gets closer and closer to 0. And then if we start down here, we start also not so steep, but here now it gets steeper and steeper. And then once we pass 1/2, it switches to getting less and less steep. So what I just said here about when we cross 1/2 should already tell you something about the type of shape the function has to have, and that is we necessarily have to have an inflection point as we go through y equal 1/2, because an inflection point is a maximum in the slope, right? The slope starts below 1/4, and then it rises to 1/4, and then it drops again when we get above. And that's exactly what an inflection point is. It's a change from an increasing slope to a decreasing slope. Okay, so we can now kind of conclude that anytime we have a high point and our solution passes that y value of the maximum, we have to have an inflection. Similarly, if we had a minimum and we passed a minimum of f of y, then we would have an inflection point of the minimum type. Okay, so let's continue with a few more solutions. If we start down here, we start with a small negative slope, and then we get steeper and steeper, always following the slope lines. And then if we start with, I'm going to just go a little bit above my graph so I have a little space to draw a curve. We're going to have to drop down rapidly at first, but then mellowing out as we get closer and closer to 1. Okay, so even though we actually found 2 steady states earlier, we can see that there's a clear difference between them, and that is all of the solutions that start in the vicinity of y equal 1 come in towards 1, and all the ones that start close to 0 leave 0. And this is going to allow us to define a stable, let's draw that in a smaller pen, stable steady state, and an unstable steady state. Okay, so a steady state is just a constant solution to the differential equation. And that, in this case, that includes both y equal, I'll put in the of t explicitly so we can remember this is a function. The function y of t is identically equal to 0 for all t. That's a steady state, and y of t equal 1. Okay, and then stability. So a steady state is stable if nearby solutions converge to that steady state. Okay, so that means that any nearby steady state has to eventually get close to our y equal 1 solution. An unstable steady state is not stable. And that's the easiest way to define it because there's a few different ways to be unstable. But if there's any nearby solution that leaves, no matter how close it starts to the steady state, it gets further away from it, then we call that solution the steady state. We call it unstable. So let me just highlight. A steady state is stable. Highlight that in red so we know what the thing we're defining is. And an unstable steady state also in red. Okay, so what I haven't shown is a different type of unstable solution. So stable solutions generally look like this one, where you have any nearby solution. If you start at any of these little red dots I'm drawing here, all those solutions will follow the phase line, sorry, the slope field elements in towards the differential equation. And really, what I'm defining here as stable, people often call asymptotically stable, but that's not a distinction I want to worry about here in this context. And then the unstable solutions, you can see no matter how close we start, if we don't start right on 0, we get swept away. And now it's possible to have a differential equation where you have a steady state, so flat line like this, and on one side you leave, but on the other side you approach. Some people will call this semi-stable because one side comes in, but according to the definition that I'm giving you here, because there are some solutions that start arbitrarily close to the steady state and leave, this is an unstable steady state. That's what I mean by it's not stable. You don't have to have it leave from all possible nearby solutions. You just need to have at least one that leaves. Okay, so that's the distinction between stable and unstable. So now what is a phase line? You'll notice that there's a lot of information in this graph that's redundant. What I mean by that is all the way across this entire line, there's exactly the same slope. So we don't actually need to draw the entire time-dependent version. We can pack that all into a single picture here. And I'm not going to put an arrow at the top like I usually would like this for an axis, because I'm going to use arrows for other things here. And this is a general feature of the phase line. We want to kind of omit those axes arrows just so they don't confuse, or maybe use a different type of arrowhead if you really need to have an arrowhead on there. So what I'm going to do here is, instead of drawing slope field elements, I'm just going to say, okay, at a large value, let's put some values on here. So we need 1 and we need 0. And then I'm going to put some values on here. Sorry, I'm going to put some arrowheads on here instead of putting these little slope elements. What this slope element says is that if I'm at y, let's say 1.5, then the slope should be negative, which means the y function, any solution, has to be going down, decreasing. So instead of putting a little slope field there, I'm actually just going to put an arrow head pointing in the direction that the slope is going. It's going down. And then as I get closer to 1, my arrows get smaller because the slopes are smaller. And you can think of the slope as being a velocity, and these arrows are representing the velocity. So as I get closer and closer to 1, I have smaller and smaller arrows. On the other side, below 1, those arrows are going to be small but pointing up. And eventually, once I get to 1/2, I'll have the biggest arrow. And then as I get to 0, I'll have smaller and smaller arrows. So this is what the arrows should look like all the way across. Now sometimes you can just put a single arrow indicating direction and not include all this subtlety of how big the arrows should be, but I'm just putting in the size of the arrow in this case to make it clear that there's faster slopes in the middle and slower ones on the outside. Okay, and then below 0, these are small getting bigger going down, negative slopes. And so when you see these arrows, it becomes clear, or should become clear, that the steady state at 1, right here, is stable. And we actually denote stability by a solid dot. So I'll fill this in. And that's going to be a stable steady state. Oops. And then we denote unstable steady state. Oops. Oh, how did I jump there? Sorry about that. We denote unstable steady states with empty dots. So here, I'll move that little arrowhead out of the way. And now an empty dot, it's a little bit hard to represent that, but fortunately I have a white pen color and I can fill that in so it looks like an empty dot. And that indicates unstable. And you can see that that's unstable because, in fact, the solutions on both sides go away from the steady state. So this line here is what we call the phase line. And I'm going to grab it. And we don't usually draw these vertically, maybe just because they take up too much space vertically. Usually we would draw them horizontally, so I'm going to take this and put it horizontally. And putting the arrow sizes is kind of optional, 0 and 1. And that is what we call the phase line for the differential equation that we started with over here, dy dt equal y1 minus y. Okay, so let's just do a quick example. So the example that I want to do here is, let's see, let me get this. Okay, yeah. The example dy dt equal y1 minus y. So that's the same as the logistic equation that we started with before, but I'm going to add one more factor here, y minus 1/2. And when I add that in, that means we're going to have an extra 0, and that's going to change the nature of our differential equation. So to draw the phase line here, I'm going to put y on this axis. I'm going to mark the zeros, which are 0, 1/2, and 1. And then I'll draw over top of those to indicate steady states and stability. Now this piece is kind of an optional thing to draw on your phase line, but it's really helpful because it gives you the information that we had in this picture. And that is on the vertical axis here, I'm going to draw the whole function, which in this case is a cubic in y with a minus sign in front of the y cubed term. So that means that the function goes through 0, going down, through 1/2, going up, and then down again once I get to 1. And now once I've done that, it's actually quite easy to draw the arrows because below 0 I have a positive slope. The dy dt value is positive, so that means the function y is going to be an increasing function, and increasing on this axis means moving in this direction. So you can think of this as a little video of a snapshot. So if I were to plot my y of t like this, and then I would have a point here, or let's say down here, negative value, the slope would be positive, meaning I'm going in this direction, meaning I'm going in this direction. And so that would converge towards 0. And then in between 0 and 1/2, I would have a negative arrow, and above 1/2 below 1, I would have a negative or a positive arrow again, and then a negative 1. And you can, if you like, put in some smaller arrows to indicate the nature of the change in slope or in velocity, but again, that's kind of optional. You get a lot of information just by putting the right direction. And now it should be clear that 0 is now a stable steady state. So I fill it in. 1 is a stable steady state, and 1/2 is an unstable steady state. And that is what we consider yet another qualitative tool for analyzing differential equations. So if you want to do a full slope field like this to see what the functions that solve the equation look like, you can do that. But as an intermediate, before you do that, this phase line is really helpful because once you have this phase line, you can sort of imagine very quickly what the function has to do in the intervals in between. So if I wanted to draw an example solution, I could now draw a y versus t graph. And let's say I'm going to start with an initial condition just above 1/2. And I have, let's say, 1 up here. So when I look at my phase line, I can see that if I'm below the well, it's not quite the midpoint, but if I'm below the maximum of this cubic, which it looks like I am here, I'd have to do some calculations to determine that, because the midpoint is not exactly the maximum for this cubic. It starts off with a low slope and then increases to a maximum slope somewhere between 1/2 and 1, and then it starts to decrease back to a 0 slope as it approaches the steady state at 1. And we have an inflection point here, right where we cross, as I'm moving here from my initial condition, as we go up towards 1, when I cross right here, I will have a maximum slope, and that's exactly where the inflection point occurs. So you get a lot of information by drawing a phase line and then translating the phase line into a y of t. Oh, let me put axes there to make that clear. This is the y-axis, y of t, and this is the t-axis here. So the order in which you might want to do this is you look at the differential equation, you draw your slope above what will be your phase line, you fill in some arrows, and then you can use those arrows to figure out what your solutions look like without ever solving and getting an expression for y of t equals some formula in t. So this is why we call this a qualitative method. Okay, so that is all I want to say right now about phase lines and slope fields. In the next video, I'm going to talk about actually using some of these phase lines ideas to get a nice method for actually solving a differential equation, in particular the linear differential equations that we looked at earlier in video 2. So that will come up in the next video.